Welcome to our webinar. This is part 2 of our MedTech series, Focus on Fundamentals. My name is Ehsan Makbari and I'm part of FUTech Business Development Team. I'm going to talk about how and why torque measurement plays such a critical role in advanced medical applications such as robotic surgery. Before we begin though, I want to bring this concept back to basics by making a comparison to amazing mechanics of the human body. Did you know that every time you rotate any object with your fingers or rotate your arm with full control of the movement, your brain performs an estimated 1 billion calculations per second to assure the precision and accuracy of your effort? Now imagine trying to replicate that action in a medical device, such as a robotic prosthetic. Instead of a brain controlling each movement, you have torque sensors that measure and calculate the moments of each turn, ensuring that movements stay smooth and exact. The bottom line is that any robotic system, and especially high accuracy surgical robotic applications, are dependent on the performance of the kind of advanced torque sensing solutions and related signal condition electronics that FUTech specializes in. Over the next 30 minutes, I'll explain the application environments these products are utilized in and cover some of the fundamentals of torque sensors and advancements that has made these products suitable for medtech environments. Before we begin, let's take a closer look at FUTech at a high level. We have over 3 decades of experience in the force and torque sensor marketplace, honing our expertise to make highly acclaimed products that are at the forefront of sensor technology. With our headquarters and manufacturing facilities located in Irvine, Southern California, our products are designed and manufactured under one roof. Having an ecosystem of multidisciplinary engineering teams, a high-precision machining center, state-of-the-art quality assurance systems, and R&D and manufacturing facilities all under one umbrella creates the ultimate collaborative platform that allows us to rapidly develop and prototype cutting-edge products. It also means that we have complete control of our production, which allows us to apply unparalleled quality standards, which not only meet but exceed the stringent ISO certification requirements. There is not an industry that we haven't supported. However, the focus of this presentation is medtech industry. The ISO 9001 certification is the baseline expectation for our industry. For those of you familiar with the medical industry, you can be assured that we are also ISO 13485 certified, which has focused on risk mitigation and source control. In addition, our calibration laboratory is ISO 17025 accredited to calibrate and certify FUTech-made sensors and other manufacturers as well. One of the reasons our company continues to evolve and adapt is because of our CEO and co-founder of the company, Jawad Makbari. A design engineer himself, he began working in the industry over 40 plus years ago and decided to start his dream venture right here in Southern California. After the Challenger space shuttle explosion, NASA recruited him to work as a test engineer in the upcoming program, the Discovery Space Shuttle. It was an influential experience that really shaped his mindset and laid the groundwork for FUTech's culture. Our saying, failure is not an option, has its roots in this work. Once Jawad founded FUTech, this reputation as a sensor guru led to more challenging NASA programs, like our involvement on the Mars Curiosity rover, where we have 2 custom solutions on the board of the vehicle since August 2012, which both are still operational. We always refer to FUTech as not only being a global company exporting to 40 plus countries, but a universal company by having products on Mars. I think it's important to highlight that one of the reasons we have a broad range of application experience is because of how our company operates. The company has 4 pillars of project engagements. We often approach application from a holistic point of view, meaning that we are not just focused on the sensor part of the project, but that we consider the application as a whole when we design a sensor solution for it. The solution encompassing the design and functionality of the sensor, as well as the output and calibration criteria needed to optimize the performance. This type of interaction means we consider off-the-shelf solution, but also a full design from the ground up. So, as we dive into the medtech end of the sensor usage, I want to start our discussion at the high level. The way we classify application use is within three different categories: capital equipment, surgical instruments, and automation tools. First, we have capital equipment, such as surgical robots, blood infusion machines, pathology equipment, incubators, or stationary systems. These tend to be larger platforms. The second is the assets or surgical instruments. This will be portable tools, sealers, drills, tools used in surgery. For automation process of consumables, think syringe production. These are made with custom automated machinery, and our sensors tend to serve as a control feedback and safety feature. And of course, there is an assortment of sensors that are used in these applications, like force, torque, multi-axis, or pressure, to name a few. When we focus at use of torque sensors in this field, there's a lot of interesting applications where these sensors are utilized. An area I wanted to focus on for our discussion is in the robotic surgical side. It's been over 20 years since the first surgical robot was launched, and in spite of major developments, this field still has a lot of room to evolve. The possibilities for advancements are fascinating, and many other startups and well established medical device companies are racing to expand the medical usage of minimally invasive robotic surgery as well as improve the technology. So, how are torque sensors serving these applications? We see a lot of applications that require some sort of haptic measurement or haptic feedback, which ties back to force measurement, which is pull and push, and torque measurement, which is twisting. Haptic feedback is not a conventional physical variable as we know. It is a combination of kinesthetic, which is form and shape, and tactile, which is texture and fine detail. And there is a lot of motivation for design engineers to build better robots or instruments to serve the surgeon. So, why is haptics so vital for the surgeon? 1. Better assessment of anatomical structures. 2. Improved tissue characterization and manipulation. 3. Reduction of suture breakage. And 4. Dexterity. This is the most important feature a novel surgical instrument can bring to the operation room and is what medtech engineers pursue when designing new surgical tools. Haptics increase robot platform dexterity, which translates into ease of use for the surgeon. This is also why surgeons are motivated to use these robots. Dexterity decays over time. We can even say that dexterity has a shelf life. If we are able to improve dexterity, we can extend the career of surgeons, and ultimately, it would translate in increasing the surgeon hour available to perform surgeries and save lives. However, besides all the obvious benefits of haptics feedback technology applied to MIRS, which is minimally invasive robotic surgery, it brings dangerous but avoidable risks. The wrong haptic feedback can lead to adverse effects. This is why sensor precision and reliability are paramount. And of course, it's not just one variable that yields to effective sensor. When we are evaluating the performance, we review a range of variables: geometry of the sensor, the components used to build, protect, and connect the parts of the system, and of course the system characteristics such as its linearity, hysteresis, creep, stability, output shift over temperature range, extraneous or off-axis load compensation. The sum of these under the skilled eye of a design engineer and technician will result in a product that will not fail. So let's explore the range of surgical tools. A good starting point is a typical surgical robotic arm. As you can see, there are multiple joints that allow for range of motion. One common application is precision motion control for torque sensors. For example, a reaction or rotary torque sensor may be used. Design engineers are interested in integrating torque sensors in these platforms as they see a benefit of additional torque feedback to each joint, which allows for improved understanding of factors that come into play for dexterity or motion control. These are a few additional illustrated examples of where we see torque sensors playing a crucial role. Starting on the left side, we see an assortment of surgical tools for gripping, pull, or a drill. We mention these as it highlights various form factors, environments, such as a high temperature going up to 500 Fahrenheit, ingress protection going up to IP68 rating, or autoclave process, which would be sterilizing the part. There are also many tools that have very small geometries that require the sensors to be embedded. I have also included an example of prosthetic leg on the far right side, as a sensor is used here for motion control feedback. While our team has had a lot of success in designing very complex and challenging custom solutions using torque sensors, we still encounter prospective customers that are skeptical about what's possible to achieve, for a variety of reasons. Some of the most common issues that design engineers approach us would relate back to size, geometry, machinability, and output. When it comes to product size and geometry, we'll show you the evolution of the rotary torque and reaction torque sensors to see how we're pushing boundaries and able to cut down the footprint of the body substantially. What we have observed over the last 3 decades is that there are increasing demand for miniaturization. On machinability, we do see that medtech applications often require a tougher standard on tolerances. We've been able to overcome a lot of these barriers by continuously investing into new top-notch CNC machines, lathe and mill machinery, and using metrology equipment that helps us measure down to microns. It also helps that we build these products within our facilities, so there is a lot of oversight and communication between the engineers and technical operators. The last note about output relates more to the integration of embedded electronics and how we are able to bundle an output that is unique to each application. Again, because we work with all of our engineering disciplines under one roof, we are able to provide an embedded electronic solution that is unique to the customer environment. Now we have spent time talking about the importance of torque measurement and application environments, but let's actually look at the products. All of our torque solutions utilize strain gauges in a Wheatstone bridge configuration to convert torque input into differential voltage output. Strain gauges are resistors that are bonded onto the flexural component of the torque sensor, and the deformation of the flexural component results in deformation of the strain gauge, which causes the resistance of the strain gauge to change. Such a signal can be converted and standardized using FUTEC signal conditioning electronics to provide analog or high-resolution digital output, for example SPI or USB, to allow communication with industrial control system or personal computers. There are 2 main categories of torque sensors: rotary torque and reaction torque sensors. In summary, a reaction torque sensor measures a stationary torque, which is static or non-rotational, and a rotary torque sensor measures rotational torque, which is dynamic torque measurement. There are no bearings, slip rings, or varying parts in a reaction torque sensor. However, a rotary torque sensor is in line with rotating parts and measures exact torque in different RPMs. I'll first start off on rotary torque sensors. Rotary torque sensors, also known as dynamic torque sensor or rotational torque sensor, are utilized in applications where the torque measurement must be taken from a spinning shaft, engine, or a stationary motor. In this case, the transducer must rotate in line attached to the shaft. A rotary torque transducer is fitted with a slip ring or wireless electronics to transmit the torque signal while rotating. They are also known as non-contact rotary torque sensor. On the screen, you'll see an assortment of sizes, some with a slip ring, other with encoder option. While the geometry of the sensor is similar, the shaft is a distinguishing factor when determining application integration. They're offered in millivolt per volt output, amplified, or digital such as USB. RPM will vary, but typically we see 3000 RPM up to 12,000 RPM. A shaft-to-shaft rotating torque sensor can be also utilized for feedback control, monitoring torque, and analyzing the motor efficiency on test stands and other types of rotating shafts. The rotating torque sensor is coupled between the motor and the load. As the shaft spins, the sensor measures the torque produced by the motor in response to the load applied to the rotating shaft. Some rotary sensors are equipped with built-in encoders. These encoders measure the angle and speed produced during the test. Torsion measurement can successfully be monitored on a local digital display, also known as torque sensor indicators. such as panel mount displays, a handheld display, or connected to a PLC or streamed to a PC using a digital USB instrument. A rotary torque sensor transducer is also a crucial part of a dynamometer, or known as dyno for short, as it provides torque measurement and angular speed, which is RPM, to easily calculate output power, allowing accurate calculation of motor or engine performance in kilowatt or horsepower, as well as its electromechanical efficiency. If you recall, one of the challenges we discussed is the demand for miniaturization. And this is not anything novel. It has been a trend in most of the applications. But while we have seen the marketplace respond to this demand, that evolution has been a little bit slower for rotary torque sensors. On the left-hand side, you can see a traditional size rotary torque sensor. Nothing unusual here. This product size is offered in 6 inches but goes up to 1.5 foot. Of course, this is not considered in medtech spaces. Even the product on the right-hand side, which measures about 3.5 inches, is still sizable for some of the joints we have to consider. This is the part we're quite excited to share with you today because we've been able to design a macro miniature rotary torque sensor. And this is one of the smallest footprints you'll find available in the market today. Here we have the same model I showed you in the previous slide stacked against our latest macro miniature rotary torque sensor, model QTA163. It's a 1 Newton meter macro rotary torque sensor with 17mm by 17mm by 32mm housing with a 5mm shaft, capable of up to 150 RPM while achieving plus and minus 0.1% nonlinearity or better. This level of miniaturization is opening up new conversations where space has been a limiting factor. One core competency of FUTEC is taking a design and overhauling it with innovation, miniaturizing and creating unique geometries to fit the specific size constraints. If you examine the available solutions in the market today have average size of 50mm by 30mm size, FUTEC macro rotary torque sensor introduced this year is reduced to 17mm by 17mm, which is a breakthrough to make some impossible projects possible now. Due to large width on traditional rotary torque sensors, engineers had to design a stack-up assembly in order to run more than one motor side by side to prevent physical interference. Today, they can design to have side-by-side mounting due to dramatic reduction on width and height, so the overall length of the assembly could be cut in half or even 1/3. So where are these products used? Here we're looking at the catheter testing, where torqueability and trackability are the objective of the test, as the catheter travels through its path, similar to what would occur in a procedure. The end user is interested to measure the position as they're feeding the catheter, and they want to know the friction and torqueability at different curves inside this path that the guide wire is traveling. For this application, we wanted to explore an alternative example that most of you may not associate to medtech quite yet: the use of unmanned aerial vehicles or drones. There is no doubt that drones have been an explosion in recreational applications, but the use of these devices are being considered for telemedicine or epidemiological monitoring. So think of an environment or areas where individuals or lab don't have access to medical supplies. Rotary torque sensors could be used inside the test fixtures as they simulate the lift of the drone. I should note that in this application, we've also utilized reaction torque sensors. So there are instances where both types of sensors may be an option. During the flight, the sensor helps measuring torque and thrust to monitor the behavior of each individual motor. This next application is more common and focuses on rotary torque sensors used in assembly with power tools. During an assembly process, it's critical to spec the torque, for example, the RPM or tightening torque and position. The encoder used would allow for this, and this information can be used to study or to define a torque spec. So tying this back to our medtech topic, think of all assortment of power tools like the drills, saws, and reamers. I wanted to return to one of our earlier slides showing you the robotic hand. Again, this is a very generic render, but it helps highlight all the areas where torque sensors can be used and how they help monitor or test the system. Micro rotary torque sensors can be used right between the robot arm and motor that engage the instrument for control, and they want to rotate, pull, or push to trigger different functions at the tip of the instrument. Those movements can be monitored with the torque feedback. In addition, they can log the torque measurement for post-analysis to see how the arm or its tools can be improved in design in this application. That second category of torque sensors are of course the reaction torque type. All of these examples have a large flange to help with installation in both vertical and horizontal positions. While the structure and the shape of the rotary torque sensor is pretty generic, the reaction torque sensor geometry has more room for play. There are multiple accessories available to create different mounting configurations depending on the application. There are capacity offerings as small as 5-inch ounces up to 24,000 inch-pounds. We always advise that you select a capacity range that is near your max torque, but that you also account for a margin in case the unit is overloaded. One feature that is possible with reaction torque sensor is overload stop. This basically is a built-in protection to help ensure that the torque sensor is not damaged if too much torque is applied. So as I mentioned a moment ago, geometry is one factor that is at play with reaction torque sensors, and this is a good overview of scenarios that are possible. On the far left, you see a typical reaction torque sensor with a protective cover and LEMO connector for quick disconnect. You can also integrate text recognition kit inside to have its own calibration information protocol. Next to this is the OEM version of the unit. Here we have removed the protective cover and you can see a flex ribbon cable coming out, or conductors could be an option. So this is ideal for high volume use, and its slim design makes it more suitable for space limitations. In the middle of the picture, you'll see a custom reaction torque sensor. Here it's getting even slimmer, but we also increase the length for adaptation to its environment. The model next to it is another custom design, and here we cut the height significantly. In some ways, you can say that this custom is based off of the very first reaction shown on the far left. This is designed for brushless DC motors, which are often used in medtech applications. I'll showcase this application in just a moment. The final model shown on the right side is another custom solution, and notice the wide inner diameter. Again, this was made for a specific application and made for a low profile use. This is used for a harmonic drive, and the flange is made for unique mounting. So here's the application where the QTA141 reaction torque sensor is utilized. This is showing you an arrangement which is stacked up against the gearhead and brushless DC motor, and attached to a flange where the assembly is floating. Here we can get a better look at the product and how there is a cavity to allow for a shaft to enter the middle of the sensor. The sensor is sandwiched between the flange and the gearhead, and as it engages with the mechanism on the right, we are able to take the measurement as torque increases. The shaft within the assembly twists the whole system, and a reaction torque sensor starts sensing the torque. And by providing that torque feedback to the motor, we can close the loop for high precision motion control, resulting in better performance. And as we explore the dynamic range of applications, the possibilities are limitless. Because of the ability to adjust the geometry and size of the reaction style torque sensors, we are able to integrate these type of sensors into a lot more environments. Starting at the left, we have another illustration of a motor and reaction torque sensor. You'll also notice that this illustration includes an amplifier aiding in the performance management of the entire system. Next, we have another dental tool. These applications usually stem from behavioral research on simply monitoring the health of a system. The sensor you see integrated is our QTA141 due to its miniature footprint. Next to the drill, we have a rheometer helping measuring viscosity. This would take place in pharmaceutical applications or chemical plants. The last illustration is highlighting torsional stiffness testing. We included this because a lot of digital devices and platforms we're used to seeing these consumer applications are now also influencing commercial design. So imagine any type of electronic device that requires an open-close hinge mechanism. This isn't exactly the most demanding type, but we felt it was important to show you scale of exciting and normal range of uses of these products. I'll close out by reviewing the example with the robotic arm. Reaction torque sensors are to be used for harmonic drives with low profile and lightweight, which can be embedded on each joint of the robot for precision motion control and improved dexterity. One big value that FUTEC offers is providing turnkey solutions. On the left side, you can see test and measurement application, where we consult the customer on catalog items, narrow down the options, and assist them to configure plug-and-play systems. On the other hand, we support OEM customers with trimming the design for high-volume production to maximize saving and shorten the assembly time. In addition, we offer to provide turnkey assembled module with in-situ calibration and embedded electronics programmed as a system, so it could be installed in the end product out of the box. I will wrap up the webinar with FUTEC's core competencies. First, miniaturization. This is what FUTEC is known for, working with customers to create unique miniature solutions for their special needs. Second, high variety of geometries. This provides flexibility for design with customization options to retrofit an existing design. Next, turnkey solutions, which we just talked about it. High precision machining center, substantial investments in various high quality CNC machines for different operations with machining tolerances in microns. And also top-notch metrology equipment such as Zeiss machines that are capable to measure down to 0.2 microns. We inspect 100% of critical dimensions of the products manufactured. Next item, traceability. With focus on medtech and aerospace, we have developed a full traceable system utilizing Oracle MRP system. From the time we receive material and serialize components, the entire manufacturing process is traceable step by step. Extensive testing. From the design stage and the extensive FEA analysis and physical fatigue testing to production stage that we perform several in-process inspection and tests such as leakage test for IP rating, temperature compensation test, IR testing, and multiple calibration tests for nonlinearity, hysteresis, and creep. And lastly, stock availability. We have great stock availability with good quantity of catalog items stocked off the shelf with the option of taking order as late as 3 p.m. Eastern Time for next day delivery. Torque sensors are critical components of advanced medtech solutions. We hope we have now shown why FUTEC's products are the most capable of meeting the high demands of these applications. Please visit our website at www.futec.com. Thank you for joining this webinar, and we look forward to hear from you.